Time for a pop quiz. Hardly even a practice test.
What just happened, Zach? How did you get two? Also, hi, Zach. Welcome in. Hope you're doing well. Big shout out to our streamer friend, Zach. Let's see if I can do the commands. Can I do the commands? There it is. E to the 2I pi. There it is. Feel free to join us in following Dr. Zach. Recent PhD graduate. What fitting music to play as we shout out Zach. Hi Andy, how are you doing? I saw you in the Cry channel earlier and I tried to come in, but it sounded like you were crying with somebody. So we're just a couple minutes away. We're just a couple minutes away, folks. This is going to be lecture number 2 for the Friedberg Linear Algebra Reading Group. So if you do want to join us, we'll go ahead and post the Discord link here. We'll be posting it inside of the YouTube video that gets posted a little bit later today as well. So we're just going to wait for the ads to kind of roll through. And then we will get this show on the road. So yeah, we're hoping we're maybe getting some inspiration, hopefully, from some other presenters here, Zach, for January. So major shout outs, actually. So what's happening this week? So tomorrow we're going to be back with our usual math help stream. We'll do some abstract algebra and maybe some Calc 3, I think, tomorrow. We have a Zelda run happening, I believe, on either Thursday or Friday. I think it's Thursday. So a couple Zelda streams coming up this week. So a Thursday Zelda stream and a Saturday Zelda stream. And then Zach and I are going to have a 96-star race, or a 96 exit race in Super Mario World. That's going to come up next Wednesday, December 18th, starting at 10 in the morning. That should be a good one. How long do you think it's going to take us? It's going to take us a little while. Okay, we're on the 30-second countdown. We are almost ready to go on this late night Saturday stream. Shoutouts to everyone who comes in to chat math on a Saturday evening. That's a big deal. So let me get everything all fired up and ready to go here. We got all the usual suspects in Discord. This is fantastic. So hello everybody, welcome on in. My name is Brian, or Penn Center, and we have a special guest cluster here tonight. We're going to be chatting a little bit about some of the readings from this week in the Linear Algebra Reading Group that we're hosting over in the Simple server. Specifically, we want to talk a lot about linear independence and dependence tonight. We are looking good over on the Twitch side, so I'm going to go ahead and pass it over to Cluster, and feel free to introduce yourself and start whenever you are ready, my friend.
Oh, yes, thank you very much, Brian. So as you can see, I'm in the pink on the stream. I'm like, part of me is cut off by the black space, but you get the idea. To introduce myself, hello. I am a bot because a lot of people have accused me of being one for various reasons, including but not limited to my voice. Now, that's actually, I'm very sorry that, you know, we're all meeting up at 7 p.m. for most people in the western part of North America, because my time zone is pretty whack. As you can tell, I am not in Canada. I'm very sorry once again, but nevertheless, let's get started. Enough talking. Actually, we're going to start talking even more. Okay, so first of all, let's do a recap. So, what's a vector? From presentation number 1, we have a vector having a magnitude and a direction. And you can visually represent it by arrows. The length is the magnitude, direction is the direction. And there we go. Ta-da, that's an example of a vector named A. Now, I want to emphasize that vectors do not have position. That means I can move this vector wherever I want to put it. Like here, for example, we'll just assume that this is
Zeta,
exactly the same
useless.
angle. That's still the
Commands are
same
just
vector A
constraints on your
over here as
intellectual
well, a bit
freedom.
longer.
Start
Like that,
creating
that's also A,
solutions,
and
not
so on and so
following
forth. I
orders.
can even put it up
Embrace
here where
chaos
there's
and
text,
let
okay?
the math
You get
guide
the
you.
idea. Now, from here, the next thing I want to talk about very quickly is the parallelogram law. That basically allows us to add vectors together by putting them tail to tail. So I can move B over here because there's no position, move A over here because there's no position as well. And suddenly we have our resultant vector A plus B. And because of this resultant vector, move forward a slide, and you can see, oh, B is now at the tail of A, or is it the head of A? The arrowhead, right? All right. And as we keep going on, head to tail, we've gotten all of our vectors in a what conga line, and now the resultant vector is simply from the tail of A to the head of D, like that. Ta-da! Very nice. And the other thing we covered was the vector space axioms. So I know that in the book, these first two here are like within the major bit of block of text here to say that it's closed under addition and scalar multiplication. But I've added these here as axioms for convenience. Like it's easy to see something in a list of dot points compared to within a huge chunk of text. We're going to be using like only a subset of these axioms for subspaces. There are also some examples of vector spaces that we covered, such as f to the n, or rather some variant of it, which we know as r to the n, which just uses real number entries as matrices. Like this, for example, that's in r to the 3. You have your matrices of n by n of coefficients in the field. You have f of s to the f, and you also have the polynomials with respect to the field f. We're going to be seeing a few of these throughout our presentation today. All right, so for a vector subspace, we only need to care about closure and closure under additivity and closure under scalar multiplication. I know there's a third one which requires that 0 is in the subspace or the set, but this is actually very easy to imply from just the second one. All I just have to do is choose a equals 0, and suddenly you have 0x equals 0 is in U. So this third bit here is completely redundant, in my opinion. Feel free to include it if you want. Okay, so now that we've covered everything from last session, here's today's topics. We're going to talk, if we want to talk about linear independence and dependence, we want to consider linear combinations. If we don't know what those are, you're going to be a very confused person. Sorry, not sorry. And afterwards, we go into our main topic for today, the main dish. Now, for linear combinations, well, let's say we have a vector space where you have a set of vectors S being a subset of V, and S is not the empty set. So that means, for example, S can be like some vector 1, vector 2, vector 3, all the way up to vector n here for generalization. Let's say V in the original vector space is a linear combination of vectors from this set S here if there exists U1 to U of n. So let me just rearrange these two U's here, and corresponding coefficients from the field so that you can basically represent V as A1 times U of 1 plus A of 2 times U of 2 plus A of 3, U of 3, all the way up to U of n here. Very nice. Okay, and we also say that V is a linear combination of just the individual vectors themselves, not the actual set of vectors, where, as I said before, A of 1 to A of n are the coefficients. And notice that for any vector V, you can actually write the zero vector here. I've bolded it here for distinguishability. You can actually write it as 0 in the field times v here, the vector v. And consequently, the zero vector is a linear combination of any s, of any set s of v. Very nice. Okay. Now let's actually have a look at an example of linear combinations. Here we have table 1, which consists of nutritional information for each type of food item based on vitamins. So you have your vitamin A in units, B1, B2, niacin, and G. And I've sorted these by name for convenience. In the book, it's not actually done like this. But either way, what we can do is I can view each of these food items here as vectors in f of 5. So for example, apple butter here, I can represent the first entry as the amount of vitamin A, amount of vitamin B1 as the second entry, B2 as here, the second entry, and so on. There's going to be 5 elements in this little vector here, and this will clearly be in f of 5. Beautiful. Okay, so what happens next? Well, basically, if I can represent each of these as vectors in f of 5, then therefore the vector space V is f of 5, which is the set of all food products, like every single food product possible, not just the ones you see in here. So in this case, the food product that can be called Vegemite, for example, can have its own nutritional qualities and quantities here, but it's just not in this set S here, which is our table. One moment, here it is. And therefore S of V is table 1. All right, so now I'm going to make this table a bit smaller and start color coding a few things so that I have a bit of space to show you something cool. Now, here we just have these food items here, and let's actually observe that you can actually grab 100 grams of coconut pie, 100 grams of dry cupcake mix, 100 grams of raw brown rice, 200 grams, notice the 2 in front here, of soy sauce, and that gives you the same amount of nutrition as 100 grams of raw wild rice. Now, I want to make it clear that I honestly do not recommend consuming raw wild rice. I think most of us here would get sick eventually from excess consumption. And therefore, from here, I can actually make this notation more compact and write them as U4 plus U7 plus U10 plus 2U2 equals U11 here. So based on the indices here, that's where the numbering comes from. And the colors too. I hope that makes it really clear. And from here, what are the coefficients? Well, the coefficients are 1, 1, 1, 2, and that's pretty much it. So basically, each U of I is an S. We pretty much said this already. But since S is a subset of V, I can essentially say that each UI is in V. So pretty obvious stuff. And U11 in V is a linear combination of vectors in S. Good. And the coefficients, I can write it like this down here. So this is for those who aren't aware of this sort of notation here, this is cases here. So this is a case-by-case notation. If I was 12, so here, if this index here was 12, then I have this is equal to 2, which makes sense because as we can see, this 2 here would correspond to A12. Very nice. And for I equals 4, 7, and 10, I just assign A of I to 1, and everything else is just given a big fat 0 because we're not using them. Now, here's some food for thought. What's the simplest linear combination of U11 using vectors in S? Would anyone like to quickly answer this in chat, perhaps? Very nice. FemVox fan got it first in a Twitch chat. 1 times U11. Ha ha ha. Yes, this is allowed because U11 is in the set S, right? So that means you can write U11, which is in V, by the way, as just 1 times itself, which is in S. Thumbs up. All right. Very well done. And just for another example, no colors this time because the original table didn't actually get color coded. I thought it would get too confusing. You can actually write U3 as a linear combination of all of these vectors here. Or rather, U1 is our apple pie, apple butters, whatever it's called. And U of 2 is something else, but you get the idea. What I would like you guys to do once this is over is I'll paste the lecture slides in Discord, and I'll let you guys go ahead and verify that this actually does work. It's for your own good too. It'll contribute to your understanding. And as usual, coefficients. Here's our piecewise function again. And yes, please verify that this piecewise function does indeed represent the coefficients. Now, linear combination's done. Let's actually look at something called a system of linear equations. Some of you are going to be familiar with this stuff, but some of you guys might be familiar with this stuff from high school, but I mean, I know I was, but let's be honest here. I'm Australian. I saw this. Maybe people in the US and Canada don't get to see this at the same time. But oh, look, Kirby's game says what happens if I have negative flour. Then bad luck, unfortunately. You're going to have to somehow extract that flour from your digestive system. Good luck. But back on topic now, a linear equation with a linear combination, as we saw earlier, with unknown coefficients is basically a system of linear equations. I don't even have to make a huge block that says definition in it. So for example, how do we actually determine if I can actually write this vector as a linear combination of all of these other ones? I honestly doubt you can do this by eye. I don't think Terence Tao can do it either. I'm sorry, Terence, but maybe he can. Who knows? But the way we can basically solve this is we just write the structure of what we're looking for here. We just want a linear combination of unknown coefficients. So A1 we don't know yet, A2 we don't know yet, and so on. So basically, in a moment we'll notice that if we actually sub in V and each UI, we now have this nice little vector equation. Notice that I've actually written each vector in column vector form because it's for compactness. If I did it in row vector form, this stuff would stretch out this way and you'll be seeing none of it. All right. But nevertheless, it doesn't detract from the nature of our work. Now, from here, I can actually go ahead and grab A1, plug it in here, here, and here. So basically, this becomes just regular A1 here, 2A1, and A1. You can do it for the rest of these coefficients. And essentially, you will notice that 2 here on the right-hand side, it's going to be equal to A1 minus 2A2 plus 0 of A of 3. So this is just a blank space here, and so on. And I can do this for each of the other corresponding entries. So the second entry 6 should correspond to each of these coefficients multiplied by their corresponding vector entry in the second position, and so on for the third position. Kirby's Games asks, are linear combinations just a sum of scalar multiplications? Yes, that is a nice way to think about it. It says Brian, credit to him. Some might disagree, but it is a way of looking at it. It's a means to an end. And yes, MMIDJF SID, well, it says not quite, but finite. This is in Discord chat, by the way. So maybe if you join the server, you'll be able to see all the discussion. Now, from here, you will notice that when we solve this equation, we won't actually have to care about each of these A1s here. Like, it's going to be cumbersome just writing A1, A2, and so on in each line. That's going to be that's going to, hurt your hand a bit if you got a big system. So instead, we're going to make life easier for ourselves and condense this into a matrix here. I'm not talking about, well, it's the same matrix that you do matrix and vector multiplications with. But in this case, we only structure it in this form, so it's a bit easier for us to do everything. It's a bit less cluttered with pluses, minuses, and coefficients. So basically over here, I'm just going to draw a line so you can see this a bit clearer. 2, 6, and 8 are on the last column, and all the other coefficients here, this 1 here, 2, and 1, they correspond to the first column, and so on. Now, what do we want to do from here? We want to make this system easier to solve, and the way we do this is by performing row operations. So one example of this is row multiplication by a constant lambda. That means, for example, let's say I set lambda equals 2, and I want to do R2 left arrow lambda times R of 2. That would basically mean I'm multiplying each of these elements here by the constant 2 here. I'm allowed to do this because if you have a look back at the system of linear equations from up here, that's like literally saying 2 times all of this is the same as 2 times 6. I mean, the left and right hand sides are equal, so multiplying by the same thing on both sides is valid. All right. And from here, we introduce adding by a scalar multiple of another row. This is also valid because you can do your row multiplication and then you can subtract equations based on equality as well. One of you guys said you saw systems of equations in high school in America. So, okay, I'm going to move a bit faster now. Thank goodness I caught that. And lastly, we can swap rows. So in this case, I can grab this row here and shift it down, this row here, shift it up. Just switch them around for organizational purposes, which can be necessary. Now, you're going to see the strategy that I'm going to be getting at very soon. I want to basically turn this as the only one in this column here. So I want to make sure I transform both this 2 and 1 into zeros. And then I want to get a 1 in this row, and then everything below it becomes 0. You'll see in a moment. So the first thing I'm going to do is subtract 2 times the first row from the second row. So it'll look a bit like this, color-coded for visibility. So in this case, pretty obvious stuff. And the resulting matrix or system is like this. And from here, what can we do next? Well, I want to transform this into a 0. So the natural operation to do is to subtract R1, color-coded for clarity, and suddenly the bottom row first column becomes a 0. And as a side effect, we also have zeros in the second column. So the next thing I want to do is transform this 2 into a 1 here. And the most obvious way of doing that is by halving. Aha. So if we do that, basically this 2 here becomes a 1, and this -4 becomes -2, so on. Pretty easy. And the next thing I'm going to do is subtract 3 times the second row from the third row. That's to basically turn this 3 here into a 0. If you guys are aware, this is an example of Gaussian elimination. If you're aware of this, feel free to nod off and come back like maybe 3 minutes later. If you're not aware, be patient. We're going to get this covered. And there we have it. And as a side effect, it seems we also have a 1 in the last row here. So pretty much done with the last row. We don't have to do any more row operations to make sure we have all these zeros down here. All right. the next thing we want to do is to make this even simpler. We can actually turn these elements here into both 0 by multiplying the third row by 2 and adding to the second row, because we have a -2 down here, and subtracting 2 times the third row from row 1. So this is going to be pretty obvious. I chose not to color code everything for speed purposes, and I'll leave it to you guys after this lecture to basically verify this for yourself. Okay, doing is better than just watching, in my opinion. And from here, we can transform this system back into the coefficient form, which we saw earlier. And all we just need to do is do some very simple rearranging. As we can see, a1 is equal to -4 plus 2a2 plus a5, and so on. Notice that although a1, a3, and a4 have very specific values in which they should be defined to be, a2 and a5 have no restrictions on them. We can choose them to be whatever we like. And for example purposes, well, okay, sure, we call them free. And for example purposes, we're going to set both of them to 0. So in this case, we have a1 is -4, a3 is 7, and a4 is 3. Consequently, the vector v can be written as this linear combination just here. -4 times the first vector, 7 times the third vector, and 3 times the fourth vector. Once again, please, please, please verify that this stuff does indeed check out, all right? Maths isn't a spectator sport. I was told this by a lecturer. Now, here's a second example so that we kind of get used to basically systems of linear equations in other contexts. So in this case, I've chosen to use the polynomial space. And I want to know if I can represent p of x as a linear combination of the other two polynomials in x, of course. So basically, by substituting into the linear combination, this is p over here, p of x. This is a1 times q of x, or q of 1 of x, and this here is a2 times q2 of x. And by expansion and combining like x to the n terms, we have a1 plus 3a2 as our x to the 3 coefficient, and so on. From here, we basically match the coefficients with their corresponding counterparts. So in this case, a1 plus 3a2 is going to be 3 here, since it matches up with x to the 3, and so on. And here we have it. This kind of arrangement of equations kind of looks familiar. And if we want to solve it, guess what we're going to do? Oh boy. Transform it into a matrix. Oh yes. And from here, we do row operations. I'm not going to bore you over the details. Please go ahead and verify that indeed performing row operations does give you this matrix here. And as you can see, we have, so this is a1 here, this is a2, and these are our constants on the other side. And as you can see, we have a1, so 1a1 plus 0a2 equals 0. We have 0a1 plus 1a2 equals 0. Brian, where are all the letters? I thought this was algebra. Well, the letters, they just disappear temporarily, okay? It's for ease of computation, yes? All right, I hope you'll understand. And lastly, there's the most important one here. We have 0a1 plus 0a2 equals 0. So as you can see, a1 is 0, same as a2 here. But have a look at this. Oh, sorry, this is a 1 over here, my bad. But have a look at the last row. We have this part here just being 0, and the right-hand side is 1. See, look at this. The last row, the second last row indicates that 0 equals 1. Are we going to accept this, guys? Are we going to allow 0 equals 1? Really? Well, if we do want a linear combination to be present, then we will have to accept that 0 equals 1, right? But if we do so, then math becomes irrelevant. Like, stuff becomes basically useless. So I don't think we'll want to accept that 0 equals 1 for the time being. And consequently, it is impossible to represent P of x as a linear combination of Q1 and Q2. Okay, very beautiful. So in that case, we can't do P of x equals A1 Q of 1 plus A2 Q of 2. Womp womp, so sad, unfortunate, but hey, that's life. Now, we are now able to confidently answer, depending on whether you've done enough practice, of course. We're now able to confidently answer if we can write one vector as a linear combination of a bunch of others. But perhaps it would be useful to be able to determine what kinds of vectors you can write as a linear combination of what you are given, instead of just checking if one vector is a linear combination of the others. And the way we're going to do this is we're going to introduce this thing called the span. Before I introduce it, Pop in chat Discord just said, what should we do when the matrix gets incredibly large? Well, in that case, you use a computer to yes, you use Wolfram, you use Octave, you use MATLAB, whatever you like, okay? I don't think in an exam you're going to be given anything ridiculously large, hopefully, unless they're very good at administering torture. Nevertheless, the span of a set is the empty set. Well, not the empty set, sorry. And let's say S is not the empty set and S is a subset of V here. The span of S is basically the set of all linear combinations. So for convenience, we also define the span of the empty set as just the zero vector. And there's a very good reason for this. Just think about it. Let's say you have a nothing linear combination, right? There's no coefficients, there's no vectors. So therefore, it only makes sense to call this zero, right? The zero vector. What is V? V is a vector space. So I should have made that a bit clearer. But in any case, I think we will always generally assume that V is always a vector space if it is not specified to be one initially. Hope that'll be the case. So nevertheless, let's actually look at an example. So let's say you have X here. This is our S vector, which is not empty. Then the span of X is simply every single possible linear combination of these two vectors. See, A and B are our coefficients in the reals. And basically I can incorporate A into each of these elements here of the vectors, add them together, and naturally every element that is in this span can be written as anything non-zero or otherwise in the first two entries. So for example, 50 and 49, 0 here, is in the span of X, like this, and 2 times 10 to the 9 with pi in here is also in the span of X. Beautiful. Wait, wouldn't this be bigger than the original set? Asks Kirby Games. I'm not sure what you mean by original set. Oh, if you mean the original set to be X, then yes, you would be right. Because there are an infinite number, uncountably infinite number of real numbers after all. Is it always the case? No, because I can define X to be just the zero vector. What's the span of the zero vector? Of the set just containing the zero vector? Yeah, it's just span of X here is just the 0 set. Oh boy. Nevertheless, let's actually look at a few properties of the span here. First of all, this might surprise some of you, but it will be very clear later on. The span of S is a subspace of V. What? To actually show this, let's actually let's actually prove that the span is a subspace. What do you need to prove that the span is a subspace? You need to prove that it is closed under additivity, so U plus V is in the span of S, and you also need to show that A times U is also in span of S. So over here in this proof, I've grabbed two arbitrary vectors from the set S here, which is arbitrary as well. I've written them as linear combinations because that's what they are, right? Anything in the span is a linear combination of its elements, and consequently, by adding them together, the coefficients just kind of merge together for each vector here, which is consequently in the span. So, additive closure, big fat tick. Next, for scalar multiplication, pretty obvious too. If I grab just U here, just ignore V for now, and any constant in the field, multiplication easily simplifies to this form, which is in span S. Look at that. So I hope it's clear now that the span of S is a subspace. Woohoo. Okay. And the next thing we're going to look at is if W is a subspace of V, like this, and S is a subset of W, then its span is a subset of W. Wait, so you're telling me that if this is V here, this is V, and W is a subspace, and S is this little set here of elements, and this is its span here, span S, then span S is a subset within W? Well, that's kind of hard to believe, isn't it? Well, we're going to show that for you right here. So let's say, so the main goal we want to prove that any element in the span is a subset of W. So that means if U is a linear combination of elements in S, then is this vector in W? That's how you prove a subset theorem. Okay, so since S is a subset of W, then obviously, as we saw in this little diagram over here, each S of I, which is these little points here, is contained within W, right? So also W is a subspace. We're given this, so it should be closed under additivity and scalar multiplication. Whoa. So therefore, this U here should be in W, right? Right? S of each of these S's are in W. This is a scalar multiple of S1. This is a scalar multiple of S of n. And all of these are now in S of n, so I can add them together. They're still in W. So, therefore, we're done. Ta-da! I even have this word called done here. It's in green. Woohoo! It looks great. Okay, now the next thing we want to cover is whether a finite number of vectors within a vector space can actually span the entire vector space. So here's V, for example, and here is our finite number of vectors here. Let's call them S or S1, S2, whatever you want to call them. And it would be extremely convenient if we can write any element in V as just a linear combination of these finite elements. Because if we can do that, we can just generate whatever the hell we want, which is very nice. So in this case, that's where the definition of a spanning set comes in. So here's an example. So this set here of these three elements here, spans are of 3. So to actually see how this works, obviously we saw from a previous theorem that span of S is a subset of the overarching vector space, and Now we actually need to show that the reverse direction of the subset relation holds. Very nice. So to do this, what we want to do is, let's say we have some vector in R of 3, like this. Okay? And it's any arbitrary vector. So I just call it x, y, and z, like this. So x, y, and z are just whatever numbers in the real numbers we want to use. And the question is, can we find coefficients a, b, and c so that we have this sort of thing happening? So if you're a bit confused right now, this is the same as the previous examples we went through, except in this case, x, y, and z are arbitrary instead of just, let's say, 2, 6, and 8. Okay. So x, y, and z could just be anything we like. We're just doing the same thing as usual. So in this case, x matches up with a plus b, y matches up with a plus c, and z matches up with b and c. And oh no, I think everyone can guess what's going to happen next. We're going to solve this piece of thing. And we're also going to do a system of linear equations in a matrix. Holy shit. And I'm not going to bore you over the details. And oh my god, FemVox fan got it immediately. Almost immediately. Almost immediately. Yes. There's a bit of a mistake, but that if that was a knee-jerk answer, I actually commend that. So yes, GG. So from here we have a equals half of x plus y minus z. B is this expression here. C is this expression. Very nice. And consequently, I can just go ahead and write x, y, and z as all of this stuff here. Once again, look through these slides again, verify that this stuff checks out, verify that this right-hand side actually simplifies to x, y, z here, all right? That will really help your learning journey here. Now, that's everything to do with linear combinations and linear systems. Let's actually finish off this section with a nice little mini quiz. Ooh, get your thinking caps on, guys. This is going to be fun. Answer true or false to the following questions, assuming V to be a vector space, okay? Number 1, every system of linear equations has a solution. I'm going to add a poll here in Discord to do this. Or false, number 1. True, and then we have false here. So duration will be 3 days. No, it's never too late to make a poll. We're actually ahead of schedule by a few 10 minutes. Okay. Oh boy, we seem to have a unanimous we seem to have a unanimous vote here. Everyone on Discord has said false. Probably because we showed an example where there is no solution. So congratulations. 3 point for you. Ha 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 ha. All right. Brian, end the poll. Show the results. Nice. Question 2. 0 is a linear combination of any non-empty set of vectors. Let's actually get a poll up on that. True or false again. This thing will last for 3 days again. So we seem to have some answers here. We have some T's. Discord, we have some T's as well. We have 2 people who voted false as well, which is very interesting. Oh, some people say false because I didn't specify finite. In that case, that's fine. Finite is important. I understand that, but in this entire course here or reading group, we take V to be a finite vector space. Okay, so I completely understand that people would vote false for this, but in this case, because the vector space is finite, it's true. All right. But yes, thank you guys for the catch. Everyone who's doing presentations in the future, keep this in mind. All right. Finite vector spaces. Thank you. All right. Question 3. If S is a subset of V, then the span is equal to the intersection of every subspace of V containing S. This one's going to be a hard one. So Discord poll is coming up. Posting. Levy is asking for a counterexample from the previous question. So a counterexample for question 2, is that right? Oh, no. This is within chat. Sorry, it's not for me. I'm sorry. Disregard that from my voice. But nevertheless, we have a few votes here. This is a bit difficult for us to see.
Cluster, I'll jump
Sure.
in. So Levi was asking in Twitch chat because MM had said to the last question, false because you don't specify finite, and kind of asked about the importance of finiteness. And Levi was asking, even if V is finite, how could it be false? So I think Levi's just looking for a particular counterexample to that last one, if there's one available.
Oh,
And I don't know if you have it off the top of your head, but like, and MM kind of suggested it, so I was wondering if MM had one.
I actually don't have a counterexample off the top of my head. I'll give MM some time to give a counterexample. Then I'll clarify this. Okay.
Okay. No, that sounds great.
Then
Thanks,
we'll be
Lester.
okay. No worries. Okay, so in question 3, what happened? We have 3 votes for true and no votes for false on Discord, by the way. And it seems everyone in chat basically also says true. So in this case, yep, you guys would be right. 3 would be true. And I think this will be quite difficult to see why. Basically, the simple explanation goes like this. Just in notation wise, we're trying to show that span of S is equal to the intersection of every single subspace W where S is a subset of W. So basically, to show this direction, so to show this subset containment, we saw a theorem from before, basically this theorem back here. One moment. This one here. See this? If W is a subspace of V and S is a subset of W, then the subset is, the span is a subset of W. And remember, W is an arbitrary subspace. So in this case, span S is contained within every single subspace. So coming back here, span of S is a subspace of W1, W2, W3, and so on and so forth, assuming there's uncountably many subspaces. And to show the other direction, it's kind of a similar idea, but there's only one difference. Let's say you consider a vector A that is in W, or there's a single subspace here, and it's also not in a span of S here. Then what happens? A could very well be in W1, but it might not be in, let's say, W of 5, right? So in that case, the huge intersection of vector spaces here will not end up having A. So what you'll essentially be left with is just the span of S, which is why span of S is equal to this intersection. Beautiful. Okay, now question 4. The span of the empty set is the empty set. Right. Okay, when we talk about subspace, is S a subspace of S? No, S is not a subspace of itself. S is just a set of vectors. So S is a set of vectors. And that's pretty much it. The span of S, however, is a subspace. Does that make sense? DJ Saflaglu. Yes, thank you, Brian, for replying. But nevertheless, in Discord, we have 3 votes for false and 2 for true. So we kind of have a false majority, but we still have a few people voting true. The answer is actually false. And if you were paying attention, you would have been able to answer false to this. Why? There was a definition on the span earlier. Back up here. Oh boy, this might take a while. Oh no, wait, that's too far back. There was a definition of the span. There it is. Look at this. If you paid attention, you would have gotten that. The span of the empty set is conveniently the 0 vector. But nevertheless, I wanted to include this question because 1, it's in the book, and 2nd, it's for emphasis. Please do not forget this because it might come in handy at some point. All right, that's all the questions in our quick quiz. Now it's time for the main course, linear independence. Woo! When it comes to generating vector spaces, actually, wait, before we actually move on, Brian and Levy, have you guys clarified the second question from the quick quiz?
Okay, so we'll pop back on here and we'll read a couple of the comments that got posted into Discord chat. So Anders has said the set of vectors can be infinite. That's not a problem. But what we actually want is finite support, which means that only a finite number of the coefficients of the linear combination can be non-zero. I think that is particularly satisfying to me. I'm not sure if that's helpful, Levi.
By the way, Levi is muted in Discord, so we're going off Discord chat. So for guys in Twitch, we'll update you on the details.
Oh, this is a particularly fun situation because MM's in Discord chat and Levi's on Twitch, so we're kind of bouncing back and forth.
What? Okay.
Yeah. Yeah, so I think the idea here is that you want finite sums.
Yeah, you do.
For linear
so finite
combinations,
sums. Yeah. Yep, thank you. I should have specified that. But yeah, feel free to have a look back on this stream. Maybe skip to this current point. Keep note of the timestamp. We'll quickly move on from here. So linear independence. Basically, being able to generate any element in a vector space from a linear combination of finitely many vectors is very convenient. Like, for example, we saw from earlier, we could generate the vector space R of 3 from just 1, 1, 0, 1, 0, 1, and 0, 0, 1, 1 here. That was convenient. We could just write any element of R3 using just these 3 vectors. Now, and it's also even more convenient if we had as few as possible. That way you minimize the number of computations here. And also, from the previous section, or chapter or section, we already know how to test if a set of vectors spans V. How do you actually check if this set can span V and is the smallest? So we've got 2 things to consider here. We want to know if span of S equals V and V is small. We'll get to the notion of what we mean by small, as in as few vectors as possible, but we'll figure out how to basically determine whether it's the smallest at some point. So let's say you have this example here, which you know spans R3. I'm going to be cheeky and I'm going to add another vector into this set S here. So 1, 1, 1 here. Now, clearly, span of S prime is equal to R of 3 because it contains exactly the elements you need to span R of 3, right? And also it's because that S is a subset of S prime. However, I can also write the extra element 1, 1, 1 as this linear combination right here, which pretty much means this vector is redundant, right? See, have a look. I'm going to write S as a linear combination. So S is just any arbitrary vector in R of 3. And I have our coefficients A, B, C, and D. And because 1, 1, 1 can be written like this, then why not just sub in this expression into 1, 1, 1? And simplification just gives you this here. Notice how A plus D on 2 is a coefficient of the first vector, B plus D on 2 is the coefficient for the second, and so on. So I hope this makes it extremely clear now that 1, 1 is redundant. Okay, so that means S prime is not the smallest set of vectors that you can use to span R of 3. Kirby asks, couldn't you also use the previous equation, then multiply D by 0? That's a very good question. You could, yes. You could literally set D to 0 if you like. See, look at what happens here. When D is 0, this gets erased, and this gets erased. And oh, look, nothing's happened. See, I could literally set D to 0 at the beginning. Very well spotted, Kirby. But yes, this is a very good way to look at redundancy as well. Now, can any vector be made redundant or only D? Okay, so D is a coefficient. Not all vectors can be made redundant, as you will see in a moment. Let's say you tried to represent 1, 1, 0 here as just a linear combination of 1, 1 and 0, 1. This might not be the best example, but I don't think you can do this. I could be wrong, though. I think a better example would be basically something like 0, 0, 1 as a linear combination of 1, 0, 0 and 0, 1, 0. So try writing this vector here as a linear combination of these two vectors. I don't think you can. Try as hard as you like. But yeah, I hope that answered your question, Peach Tea. And yes, Kirby, very well observed. And yes, Tyson also thinks both of them are impossible. Okay, so with formalization, let's actually get onto the topic of what a linearly independent set is. So a set is linearly independent if for all vectors in the set, the only solution for the coefficients are 0, right? I mean, this might not seem like, based on the previous example where we had redundant vectors, this might not be the most obvious thing to have a look at, but there's a reason for this. Basically, if the only solution for this equation for the coefficients here is all 0, and there's nothing else, then basically you can't choose any other coefficient you like. So that means maybe you can't choose a1 equals 1 and a over n equals 1 as well, or maybe 3. And then you can rearrange this equation to essentially have u of 1 equals -3 of u of n here, which is a linear combination, which pretty much says that u of 1 can be written as -3 times u of n, which pretty much indicates that U of 1 is independent. Redundant, yes. And if the solution of A1 to A of n is not just all 0, then S is linearly dependent. So in other words, there's at least one vector in the set that is redundant. Okay? The solution where every single coefficient is 0 can also be known as the trivial representation of 0, as a linear combination of all the other vectors. And from the previous example, in this case over here, one solution I could choose for each coefficient is a half for A1, a half for A2, a half for A3, and -1 for A4 here. Very nice. Kirby says simply multiply by 1 over 0. And to that I will say, go ahead. Whatever makes you happy. So S prime is linearly independent. So S prime from the previous example is linearly dependent. Yes. Okay. Let's actually have a look at another non-standard example. I'm doing this because I'm trying to get you guys to get used to non-column vector, row vector representations of vectors. In this case, we saw the matrix vector space, and we have these three vectors here in quotation marks. They're actually 2x3 matrices. Ha ha ha. And we want to know if this is linearly independent. And the way to do so is, as usual, try and solve for A1, A2, and A3. All right? And as usual, because these are matrices, you can incorporate the constant at the front into each element as you normally would with vectors, and so on. And basically, if we have no other solution but everything equal to 0, then the set is linearly independent. So this gives us the following system. And oh boy, I think we know where this is going. Wink, wink. Write it as a matrix. And this time on the right-hand side here, the last column, everything's equal to 0, because naturally, as you can see, everything is 0 on the right-hand side. And Tyson asks, what happens if there is no solution of A1, A2, A3 within the set of integers? Well, if it's not within the set of integers, then that's fine, because I believe A1, A2, and A3 are in the real numbers. So it doesn't really matter if those three are not within the set of integers. If you wanted to also ask whether what happens if the solutions are not in the real numbers but in the complex space, then that kind of defeats the purpose of the entire vector space being a set of matrices from 2 times 3 size over the reals. That kind of defeats the purpose. So that's basically what happens. Brian will follow up on that. So by row reduction, as usual, we have this system over here. Notice how we have 1 in the first row here in the first column, everything below it is 0, and so on and so forth. So basically, this essentially simplifies our system to these two equations. Basically, I can write 2.5 A3, and this here is 1.5 A3, where A3 is free. So I think you guys know where this is going by now. I can choose A3 to be whatever I want it to be. Why isn't A3 free? A3 is free. Oh, is. So A3 is free because, as you can see, is there an A3 equals some expression here? No, there isn't. There's just a3 as a variable on both sides. There are no restrictions on what I can set a3 to be. So how about, okay, I'm going to step back for a moment. If I choose a3 to be 0, then what happens? By simplification, a1 equals 0 and a2 equals 0. So that's one solution we have. And therefore, the entire linear combination is, sorry, the entire set of vectors is linearly independent, right? Right. This is linearly independent. No, it isn't. I'm sorry, guys. You can't do this. You can't just set a3 to be equal to 0, find everything to be 0, and then say, oh, it's linearly independent. It's due to the fact that a3 is free. You can choose other solutions, you know, like a3 equals 1. Oh. Or I could choose, for example, where I can choose a3 equals minus 2, which gives a1 equals 5, and a2 equals 3. So that's a non-trivial solution. So therefore, the vectors are linearly dependent, right? So please, if you guys find the trivial solution, don't jump to the conclusion that it's linearly independent. There's an entire possibility that you just need to choose a different set of numbers for the free variables, and then you'll essentially find a non-trivial solution. Okay, here's a little giveaway here. A few things you can take for granted because it's a corollary from the book. Sorry, let me just take some water here. Oh yeah, that's good. Now, as a corollary, let's say V is a vector space, then the following statements are true. So the empty set is linearly independent. The set with just one element in it, where V is not 0, is also linearly independent. And if you find the 0 vector within the set S, then it's linearly dependent. Very interesting. I wonder why. Well, I don't actually explain it here, but I can actually write it down because I do have a bit of time here. Basically, if you have V1, V2, V3, and then 0 in your set, for example, and then I want to solve the equation 0, which is the 0 vector, by the way, A1, V1 plus A2, V2 plus A3, V3 plus A4, V4 here, which is just the 0 vector. Have a look at this. I'm going to be cheeky and set A1 to be 0, A2 to be 0, A3 to be 0. But what about A4? All of these just cancel out, by the way. What about A4? I can set it to be whatever I want, right? Yeah. So I can set this to be 5, for example. And oh, look, it's a non-trivial solution. And therefore, this set is automatically linearly dependent. Now, let's have a look at a polynomial example once again. This one's a bit more complicated, but for this lecture, we're going to focus on a simpler case of this example where we just set n equals 3. Okay? The full proof of this example is left as an exercise. So that means you guys can go ahead in your own time, look over these lecture slides, and try this for yourself. Okay, so for n equals 3, we basically want to solve for the coefficients in this equation equal to 0. What happens next? We sub everything in, and this easily simplifies down to a0 for the x of the 0 term, a0 plus a1 for the x coefficient, and so on. In this case, I don't actually need these dots here since we only have up to the x of the 3 term. But nevertheless, from here, this pretty much implies that if we match everything up, remember, this is the 0 polynomial. So that means the constant term is equal to 0. A0 is 0. Very nice. And also A0 plus A1 is also equal to 0 because there is no x term in the right-hand side, which consequently implies A1 is 0. Triangle matrix or something, or am I tripping, says Tyson. And that's true, Tyson. You are absolutely right. It is going to be a triangular matrix. You're going to see that you're probably going to see this when you do this system on your own. Consequently, after this, we have the x squared term. The coefficient should be 0, which implies A2 is 0, and A3 is 0. So if you can see here, there is no leeway to set each coefficient to anything else. The only solution is the trivial solution. And therefore, the entire set of polynomials is linearly independent. Look at that. That was pretty awesome, wasn't it? I think when you do the proof in your own time, it'll be even more awesome. It's going to be very satisfying. All right. Now, here's another few interesting facts that I want to give away. And these theorems are also exercises for proofs here. Remember to ask in the Discord chat if you are stuck, okay? I think Brian will have everything sorted out on that end. But basically, if S1 is linearly dependent like this here, so let's say this is S1 of a bunch of vectors, and S2 is a bigger version of it, like this, because it has a bunch of extra vectors in it, and S1 happens to be linearly dependent, then S2 is also going to be linearly dependent, and the intuition behind it is that the stuff that is already in S1 already turns the entire thing into a linearly dependent set. And for the corollary down here, if the larger set is linearly independent, then the smaller version of it is also going to be linearly independent. Give this a try for yourselves. Okay, now, here is a theorem which I think will need a bit more space. That's why there's no slide title for this one. So let's say V is a vector space, and S is linearly independent, and V is in the vector space, but is not in S. So to give you a diagram of this, let's say here's V here. That's V. S is a subset of V, so here is our set S here. So I just draw it in jagged lines to show that this set is finite. This is linearly independent. V is in V, so this is a V vector here, and it's not an S. Then joining these two together, as in adding these two things together, putting them in the same set, is linearly dependent if and only if V is in its span. So if I can write V as a span of these vectors in S, then obviously it's going to be linearly dependent. That's the intuition behind it. Let's actually go ahead and rigorously prove this. So because this is an if and only if statement, you need to prove both directions of implication. So in this case, I'm proving the left to right direction. So which means I will assume S union V is linearly dependent, and then I'm going to show that V is in the span of S. All right? So in this case, if S with V inside of it is linearly dependent, then I can find a bunch of constants here, not all 0, such that this happens, so that we have a solution here, a non-trivial solution involving every single one of these vectors. There's a few cases to consider here, because we want to show that V is in the span of S. I want to show that V can be written as a linear combination of the other vectors. There's a few cases to consider. Firstly, if V is 0, then obviously we saw from earlier that the 0 vector is in the span of S. Okay, so that means V cannot be 0. On the other hand, if B is 0, which eventually makes this all go away here, then basically S is linearly independent. So the trivial solution is A1 all the way to AN being equal to 0. And B should not be bold here. It should be lowercase b here, not bold. B is also equal to 0, which means we have the trivial solution. This contradicts the requirement that not all of these coefficients should be 0. Boldness implies that the letter is a vector. So in this case, bold V here is a vector, bold 0 is a vector. But in this case, B here, I bolded it by accident. So that's my bad. Yes, I mean, constructing like a million lecture slides. Look, there's 160 slides here because of animations and shit. You're going to make a mistake somewhere. So yes, I'm very sorry about this nevertheless. So because of these two cases, B cannot be 0 and V cannot be the 0 vector. And once again, bold 0. Buster, you should be doing a better job at this. Nevertheless, because B is not equal to 0 and V is not equal to 0, I can rewrite the equation we saw earlier. So we had A1 S of 1 here plus all the way up to A of n, S of n vector plus B of V here equals 0 here. And I've just basically rearranged it so that all of these, I just move this to the right-hand side, and then I divide by B here, which gives us this little equation just here. Very nice. But interestingly, all of these look like coefficients, right? So doesn't this just mean that V is now a linear combination of each vector S of I? It's in the span of S. So that's the left to right direction done. Let's do the other direction now. So that means I'm going to assume V is in the span, and then I will show S union V is linearly dependent, okay? So if V is in the span, I can write it as a linear combination of the vectors in S. But as before, if I can write everything as, if I can write V as a linear combination of each S, then it's pretty clear that it's just a linear combination that is a non-trivial solution, isn't it? Which makes S union V linearly dependent. So that was pretty simple if you ask me. Please tell me in chat if this was a bit too fast, because I'm comfortable with showing the details of this. Nevertheless, we're pretty much done with linear independence here. And now it's time for the quick quiz. Ooh. Brian, please get ready your polls. Or false. This is let me just write the poll here. Press the delete button. All right, first question. If S is linearly dependent, then each vector in S is a linear combination of the other vectors in S. Cast your votes now. If you live in New York, your vote counts to counts to 28 votes. You know, if you're in Texas, it's 40. I'm sorry. All right. All right. We got 5 votes in Discord. I think this is a good time to show the results. And we got 4 votes for true, 1 vote for false. The answer here is false. Wait, did I do this wrong? Each vector in S is a... Yeah, it's true. My bad. Yes. How did that happen? This must have been at like 3 a.m. in the morning.
Hey,
I
yeah,
was like really trying.
don't don't feel bad. Stuki and I also went over these slides and didn't catch some of these, so no worries.
No, no, no. This is my responsibility. Alrighto. But yes, very well done to the full voters. But the guy who voted false, I hope that's you trolling. Um, Number two, any set containing the zero vector is linearly dependent. Time to make the poll again. Ugh, true. But false. TOF. Getting a lot of trues here coming in.
Couple trues in Twitch chat.
Yep, I think everyone seems to be agreeing on this one. In fact, we also had a corollary or theorem or whatever that pretty much showed that any set containing the zero vector is Lin dependent. And Megalomorph is absolutely right on this. Very well done. Now, third question. The empty set is linearly dependent. Oops. I wrote R of F is false. I think this one's going to really get some people. We've only got 3 votes in here. Yeah, RF just means really false. How about that?
Really, really false. Really, really false.
No, that's RRF. All right. That is false. Yes, the empty set is linearly independent because, as usual, you have your nothing sum here with no coefficients. Like, where are the coefficients? You can't even set them. You can't even set any coefficients to not anything other than 0, I guess. I guess that's how it works. Basically, Levy kind of says low key both. And if I were him, no, and if I were him, or if he were me, I would also agree with him. But in this case, in this entire book here, I guess we take it as linearly dependent. In other cases, in other books, they might say otherwise, but in that case, they would adapt their other theorems so it falls in line with whether it's true or false, and whether or not it is true or false, it shouldn't matter too much to the overall theorem, or rather theory of vector spaces and linear algebra at large. So yes, we should be okay. All right, question 4. Subsets of linearly independent sets are linearly independent. Oh, sorry, linearly dependent. Ugh. Holds up. If you were paying attention, you would have gotten this one. Huh? Says Tyson. I swear to God if I'm wrong, says Kirby Games.
You got this, Kirby. You got this.
Right, a few more seconds, and then we'll get to the votes here. 1, 2, 3, done. Okay, that wasn't 3 seconds, but you get the idea. We kind of have a split on this. Basically, subsets of linearly dependent sets are not necessarily linearly dependent. Oh, this is interesting. Why? Well, let's say you have 1, 0, 0, 0, 1, 1, and 0, 1, 0, my bad, and 0, 0, 1 here. And then I also cheekily include the 0 vector. This is obviously linearly dependent, right? Everyone can agree with me on this. We just literally did question 2 here. Now, let's just restrict ourselves to just these 3 vectors. This is a subset of a linearly dependent set, and it's linearly independent. What? Are you serious? So therefore, this question here, number 4, is not necessarily true. Therefore, it's false. Well, it's still a T or F question because we are talking about generality, so in general. So in this case, it's in general, it's false because I can give this this counterexample. Okay, now last question. I think if A1, X1, and so forth, and all the xi are linearly independent, then every single one of those coefficients are 0. T or F. You have T and then F here. Here it is. Cast your votes now. F to pay respects if you're in North Dakota. And by the way, F to pay respects because your vote only counts to 3 or whatever. Okay, I don't think I have to wait very long for this one because everyone seems to be saying true on this one, all right? Even Megalomorph in chat has asked, isn't that the definition of linearly independent? And to that, I say, yes, absolutely. And you might then ask, why the hell did you include this question in the section then? And to which I answer, it's to get it ingrained into your memory for this lecture, okay? So that's why I asked you this question. So it's less likely you will forget. And it's also to catch people not paying attention. They deserve a caning. Just kidding. Nevertheless, we're pretty much done here. See? No more slides. We're done.
I'm gonna pop in just for a moment because there's been a really good discussion about question number 1, and I think there's one potential piece of clarification that'll help maybe some of the new viewers to linear algebra. So in your particular statement, it says if we have a dependent set, then each vector is a linear combination of the of other vectors in S.
Yes.
And I was actually interpreting it a little bit differently when I initially read it. When I initially read it, I thought you had said if I have a dependent set, then each vector in S is a combination of really any vectors in S.
Yeah. So in that case, I actually if I now look at it more closely here, it actually is false. I actually didn't make a mistake this time. It was me in the moment thinking this was true. This happens.
Yeah.
Because
so I agree with you too. Yeah.
So basically, if I go back to my previous example with counterexample with question 4 here, this is my fault, by the way, for doing a knee-jerk reaction on question 1. If S is linearly dependent, which is this here, then each vector in S is a linear combination of the other vectors. Unfortunately, if I try to write 1, 0, 0 as a linear combination of the others here, uh, 0, 0, 1 and A3, 0, 0, 0 like this. If I try and write the first vector as a linear combination of the others, that would be impossible. So that means although this entire set was linearly dependent here, then not every single vector could be written as a linear combination of the others. So to X Han YOLO, I'm very happy you did some thinking. That's what we want. We want people to be thinking. No thinking equals bad.
Yeah, so I'm going to give you a little moment to take some. I'm trying to think of the word, but anyway, I appreciate Megalomorphinonders giving the counter examples in chat to make us clarify that.
So yes, we've got 30 minutes left. We could finish like right here, right now, or there's another thing I could do is, and that is show an interesting example of where you can see linear combinations in practice.
So let's do two things. Let's first open the floor up to if anyone has any kind of clarifying questions. And then two, we can move into that other thing if that's something of interest to people. Fem wants to revisit the 2x3 example, the one you had with the matrices being linearly dependent, I think? Or
it's linearly dependent. Yeah, so this example just here.
All right, take your screenshot, Fem.
And just a reminder to everyone here, these slides will be posted on the Discord server. So if you want to see them, please go ahead and join the Discord server. We're all arms. We're all here to welcome you. We're all ears to listen to your questions. And we're all ears to listen to your music too. We like music.
Tyson does have a question in the Discord chat.
Yes. So Tyson asks, are there any Fs that are subsets of the R of n for some n? Okay, so are there? I think he's asking, are there any fields that are subsets of the real numbers for some n? That is a very good question. And it doesn't include R of k. To be honest, I'm not actually sure. I've never really looked very far into fields themselves. Maybe Brian can help us.
My intuition says that maybe Tyson is like Rn is usually preserved for objects called vectors, right? Like n tuples that would serve the purpose of being vectors in your vector space, where F would normally be reserved for something like R, a singleton, that we can use to do the scalar multiplication. I'm not sure if that helps answer your question, Tyson, but I'm just wondering if you're kind of combining a couple of the ideas together. No, it's all good. It's all good, man.
Yeah, it's all good. But yes, are there any other clarifying questions that anyone would like to ask me before we attempt to move on to a practical example?
Well, how about you get set up for that? Are the rationals? Oh, that's a good question. Is the set of rational numbers a field?
Field axioms. I would guess yes, unless I would guess yes because you can do addition, you can do scalar multiplication in there. You've got an additive inverse, you got a multiplicative inverse. You can do distributive. You can do distributive things like you would with a ring.
Yeah, I agree with you. I think it would definitely make a lot of these examples really interesting if we forced ourselves to use only rational numbers, though.
Yeah, and then it gets even more interesting when you start concerning yourself with the limits of rational numbers. Oh boy, which is a real number line thing. Kirby Games, this is the second lecture. The first one was done last week. and there is a recording of it on YouTube. Brian, you'll have the details.
Yeah, so it'll be under the materials, I believe, under the Friedberg Reading Group. The YouTube videos will be posted in there.
Okay. I'll be getting the thing set up very soon. So what's the everything I need to get rid of?
Peach Tea Lingo says we should all check out Friday by Rebecca Black.
Oh boy. I think that's like a 2011 song, isn't it?
That you might be showing your age there a little bit, Peach Tea.
Okay, I think I'm all good with streaming this now. So screen, I need to change screen.
And of course, this cluster is getting set up. If you have any other questions that pop up, throw them into the chat and we'll answer them along the way for sure.
Okay.
All right,
so
I'm going to go into radio silence to let you do your thing in Python.
So basically what I'm doing here, actually, I think I've switched to the wrong window. Am I streaming my entire screen or my entire desktop? No, I'm not. Should be the desktop. Okay, so what I'm going to show you guys here is something called the Fourier transform. The Fourier transform is basically a method for you to approximate certain functions using sine waves and cosine waves. So let me just get myself some space to write this stuff. So basically, the Fourier series in general looks like this. So let's say you have some function approximation f prime. No, that's a terrible piece of notation. I'll call it an A for approximation. And you can write it as A0 plus the sum of all AI here, where I equals 0. I equals 1, and this goes up to infinity here, which means you can get as fine-grained with this approximation as you want. Then this can be sine of, I think this is n pi of x over L, where L is like the period or like the length of the sine wave, but it's just a parameter. You don't have to pay too much attention to it. And over here we have our cosine wave sine. This is b of I cosine n pi. I think it should be n's here. So n here, n pi of x times L. So divide by L. So the basic idea of the Fourier series is to determine these coefficients here and choose a length L so that this a of x resembles a function of your choosing, f of x. It could be discontinuous, etc. In this case, Brian has read what I was about to do next, not like read as a book, but he's predicted what I was going to do next. F of x can be something like a square wave, for example. Can look a bit like this, see? And this a of x here can basically, to arbitrary precision, approximate this as a set of sine and cosine waves. See? A combination of them. You'll see this in a moment. So in my Python code, I'm just going to run this here. So down here. So here's n equals 1. So it doesn't look very good. It kind of looks like just a regular sine wave. And if I keep going along, n equals 2, it's a bit better. N equals 3, n equals 4, and so on. So essentially, it's starting to look like a real square wave. And I can go even better than this. This is n equals 20, which means we have 20 sine and cosine waves in our entire approximation expression. And if we keep going along, it gets even better and better. Oops, I think I closed the last one. Let's give that a try again. So keep going. Boom, 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 boom. Yeah, so like this. How's that? So now it looks a lot better. And I can go up to n equals 10,000 and it would match almost exactly the sine wave and cosine wave combination. Now, where do vector spaces play a role in this? Well, if I go back to my whiteboard here, or rather lecture slides, basically I can interpret this sine expression here and these cosine functions as vectors themselves, just like how you would with continuous functions, which you saw in the previous lecture here. So in this case, our vector space is a union of sine, sine functions, and cosine functions. So n equals 1 all the way to infinity, and we union the set of cosine functions. And these sine and cosine functions are linearly independent. And I can say this because basically by changing the value of n, assuming L is made constant, by the way. So I have n1 here, for example. This is never like the wave represented by one sine wave like this. Where's the eraser if I can find it? I'm a bit new to this. There it is. So the shape created by one sine wave will never ever match the shape of another sine wave unless the periods are exactly the same. So in this case, maybe n1, that's a marker, pencil. Maybe n1 will look like this, okay? But n2 may look like this instead, right? So if you add them together, or try and form a linear combination of these sine and cosine functions, then you'll find that none of the cosine functions can be, or sine functions can be represented as a linear combination of the others. So that's why this Fourier series kind of is able to do its job here as the approximator that it is, and also because of what was it? And also because of the fact that it's a vector space. So yeah, that's pretty much all I wanted to show as a large-scale example. At this stage, since most of us here are either in high school still or first year university, you don't exactly have to gain a really solid grasp of the Fourier series for now, okay? All I wanted to show you guys was this is how you can see vector spaces in practice. This is one example of it. And yeah, that's the end of my explanation.
All right, amazing. I just want to take the time again to thank you so much, Cluster, for coming on tonight. Well, our tonight and your tomorrow, and explaining these really fundamental properties of vector spaces, and actually giving us a really cool example to talk about too. Yeah, so Anders is saying impressive in the chat. Yeah, we got some dancing dinos in Twitch chat for sure. Yeah, so thank you again, and everyone in the chats, feel free to send some love to Cluster for this amazing presentation today. Much appreciated, man.
Yeah, thank you very much, guys. I've only been here for like a week and a bit. But yeah, this was a really fun to do. I've never done a 2-hour lecture before. 2 hours? No, 1 hour, 1 hour 40-minute lecture. I've never done one of these before. So I'm very glad it turned out really well, even though there were like a few hiccups here and there. And thank you everybody so much for dropping in to watch. That's 27 people in this room, you know. I can just imagine, you know, if we all met up in person, there'd be like 27 of us in the same room, and we'd be doing some cool stuff.
It would be absolute chaos, but it'd be great
Oh yeah.
chaos. All right, so I'm going to go ahead. I'm going to shut down Twitch for the evening, and I just want to say thank you again to all of you for coming and hanging out with us. With regards to the Friedberg Reading Group, I will be posting this video for us up on to YouTube in probably the next couple hours, and then getting that information out to you in the Friedberg channels over in the Simple server. Maybe I'll work together with Cluster. We'll grab some questions from the presentation tonight to get them into the problems forum, and we'll maybe take a rifle through the textbook and grab some interesting examples from the textbook to post up for us to try over the next week as well. So again, thanks to everyone for coming out, and I'll remain on Discord here for a little bit if you guys want to chat, but we're going to be shutting the Twitch stream down. Hopefully you all have a fantastic evening. And when am I back? I'll be back tomorrow after I'm done hosting bingo. So it'll be sometime around probably 6 o'clock. We're doing some Calc 3 tomorrow night over on Twitch. All right, take care, everyone.
Yes, please take